us today. We're back for the second part of this block, focus on state transfer and measurement in optomechanics. I'm delighted to have two really excellent and exciting talks. So before we start on that, just a few things. So this will be last block, and then we'll of course have a bit of a break after this block, and then we'll be joined for our next set of talks in April. House rules, of course, always apply. If you have questions, if you're joining us for the first time on YouTube or on Zoom, please forward your questions in the chats, and then I'll take note of them. If you're joining us via Zoom, of course, you may raise your hands after the talks are finished and Q&A starts. So let me start by introducing our first speaker. So Niccolo is a PhD student in Simon Groeblacher's group in TU Delft, and his work in essentially teleportation and its uses in optomechanics. And he's got some exciting, really exciting work to present, and so I'm really delighted to have him here. It's a real honor and privilege. So without further ado, Niccolo, it's your platform.
Thanks for the kind introduction. Let me just share. So here we are. Let me have the list pointer. So thanks so much, everyone, for joining. As Rashid said, I'm Niccolo Fiaschi from Groeblacher Lab in TU Delft. And today I will talk to you about routing quantum information via optomechanical devices. The idea of this part of the Groeblacher Lab is to work towards the quantum internet, or a quantum network in general. So there's the need of having two type of communication of state transfer in this quantum network. One for the long range, and in this picture is the space between node, and is in a distance of more or less the 100 kilometers of distance. And one of the most famous protocol is the VLCZ protocol that is depicted here in this quite famous paper of 2001. But there's another one also. There is the so-called on-chip, so with a scale of centimeter, and is inside the node. In fact, like this is a quite nice paper that that makes this sparse array configuration for quantum computer. You cannot scale quantum computer limited to the infinite, so it might be better to have like connection between this array of quantum computers on chip. And I would like to talk in Groeblacher Lab that we are trying to tackle these two challenges via optomechanical devices. So in the first part, I would like to talk about the optomechanical quantum teleportation. That is a paper recently published for the long distance communication. While in the second part of the talk, I would like to talk about these two papers, one that is on the archive and one that will be soon in the archive, that wants to go more in the direction of connecting on-chip structures. So with no further ado, I will just make a small introduction of the optomechanical device that we use. It's a silicon nanobeam with an optomechanical crystal with a defect in the center that co-localizes the mechanical reading mode at 5 gigahertz and the optical mode in the telecom band. What we do is that this is an optical waveguide to just address that optically. What we do is that we cool it down cryogenically in a dilution refrigerator at 10 millikelvin, so that we can deeply initialize the mechanic in the ground state. That's the basics. The other basic is the DLCZ protocol, or entanglement swapping, that is based on starting with two pair of entangled system. In this case was done with atomic clouds, but I will explain that it will work the same. And then swapped entanglement to have this left and right cloud entangle at long distance, that they never directly interfere. So in our case, it will look like this, that you can see that instead of atomic cloud, we have these little nanobeams, but it works the same because the atomic cloud, they have a lambda system, and with the Stokes anti-Stokes scattering, and we have exactly the same system in quantum optomechanics, that we just have the right and read protocol with the lambda system given by the optics and mechanics. So in this case, we have again the two mechanical nanobeam that will be entangled, and then you perform the entanglement swapping like via the Bell measurement in the middle to have a long distance entanglement. So, well, exactly, this is to compare the two images. What we have done in the past is a famous paper of 2018 from our lab, where they performed the first entanglement between the two mechanical oscillator. And recently, another paper from our lab, we proved that these mechanical nanobeams are very good quantum memory, with native telephone wavelength still the highest T2 star ever measured. So the next step would be to make this entanglement swapping. Well, as you can see from this image, we have to change something compared to this previous image. Because if we really want to teleport a state, or if you really want to encode information, actually one nanobeam is not enough, or in this case, one atomic cloud, but they work in the same way. So what you need is, you need, as registry, you need two atomic cloud with two nanobeam. And for example, one of the easiest encoding is in polarization. So one is polarized H and one is polarized V, for example. In this case, this is the entanglement generation, and here is the entanglement swapping, where you start with, again, two entangled system, and then you perform the swapping in the center. The Bell state measurement here is quite complex, is just a very fancy protocol to cancel some higher order excitation, but it works basically as the same way as the Bell measurement before. So what we had done in our experiment of the teleportation is to make this first step before the entanglement swapping. In our case, we made like some changes in the setup. The first is, as you can see, replace the other source with a single photon source that was coming from a weak coherent state, so from a heavily attenuated laser, and we just modified the Bell state measurement to have it simple, but it works exactly in the same way. The reason for this is just to have the higher rates of the teleportation and to have the setup much more simple. So this is coming from the paper. As you can see, we have, instead of the two atomic cloud, the two nanobeam that compose our registry. One is polarized H and one is V. They're combined, and here where there's the Bell state measurement, the state to be teleported that is coming from the laser are interfered with the light from the nanobeams. I will not go too much in the details. It was quite challenging experiment. This is the final result. We choose the 4 basics because of the symmetry of the system. We don't need to perform in all 6 of the block sphere. And this is the teleportation fidelity for the 4 bases and the average. So there is a threshold, that is the classical threshold, that is 2/3, that we beat from in all of them, and in the average also by 4 sigma, if I remember well. And the only thing is just to take this measurement took 1 month. So the teleportation fidelity is just the ratio of the total event that you have divided by the event where you succeed. So this is just a measure of how good is your teleportation protocol. And of course, even if it's quite good, it takes 1 month. So we still need to perform some adjustment in the system and to improve the system to perform the next step. That will be, for example, this entanglement swapping. So this part is still a work in progress. We hopefully soon will make some new work on the long distance, but we are currently working on another type of state transfer. That is the one on chip, so in the centimeter, millimeter scale. That is, for example, to connect this sparse qubit array. The work that I will talk about is the non-classical mechanical state guided by phononic waveguide and the on-chip distribution of quantum information using traveling phonons. This will be soon in the archive. We're actually finishing to write it right now. So the idea is to have a slightly different design of the device. The optomechanical cavity is basically identical. So as you can see, this part here, the device is still with a colocalized mechanical and optical mode, still at 5 gigahertz and in the telecom band. But this time we have modified the structure to have a very long waveguide here, so that the optics is still confined, but the mechanics can leak and travel in the waveguide. So it's effectively a waveguide just for phonons, a single mode waveguide for phonons. And we can make it roughly as long as we want. We can go to millimeter if we want, but generally, like, we end up with a mirror for phonons, so just a freestanding end, so that the phonons are reflected back. And roughly is on the order of 100 micron, 200 micron length. Then we, as again, we cool it down to deeply initialize the ground state, the mechanics, to perform all the experiments that we want to do. So the system, you can understand that is basically a cavity for phonons and another waveguide that is, since there's a nanometer at the end, is basically just a very long Fabry-Perot, again for phonons. So the mechanical spectrum you can imagine is something like this. It's just the hybridization of a single mode cavity with the Fabry-Perot mode of the cavity in a certain span. So it should be a roughly equally spaced mode in a certain band. So if you Fourier transform, or if you look at the device properties in time, you would expect that the pulsed excitation will leak out from the cavity and will be reflected back and go back in the cavity at certain time that will be equally spaced in time. This is coming from the paper. This was the peak, the bouncing peak, so the reflectant, the echo peak that we used to perform the experiment that I will explain soon. And this is just a cartoon picture to visualize a bit better what it happens. Like if you send an optical pulse to write the excitation can is created in the cavity, then leaks in the waveguide, it bounces back in the cavity, and then it can be remapped again in an optical field. The first experiment we have done is a cross correlation. Cross correlation means that you write, so you send a write pulse to create one excitation, and then you remap it, and then you check, and then you look at the G2, so the correlation between the two fields. And what we get is that we have uncorrelated or at max classically correlated field when the pulse is outside the cavity. So when, for example, the pulse is traveling still in the waveguide, so it's not again in the cavity, but when the pulse is in the cavity, we see a quite strong non-classical correlation. So that means that we actually create this non-classical state. It travels in the waveguide, then back we can retrieve this non-classical state. So this was the first work in this direction. But then we said, okay, this is very good, but it tells nothing about, for example, the coherence of the state. This is just, cross correlation is just checking clicks at the end. It doesn't tell you anything about the phase, so the coherence of the state that it travels. So we went back, well, okay, yes, this is the result is 4, there's 4.4, that is way above the classical threshold. So we went back and we start redesigning a bit the structure to have better properties. And as you can see, it's pretty similar to before. It's still along this long waveguide, but we redesigned completely the way that it is connected to the substrate. Now it's connected, completely connected. Every period is connected with this clamp shield that a full band gap around 5 gigahertz. and it works the same. We have a mirror at the end. The length is more or less, again, in the hundreds of micron. And we put it, again, in the dilution refrigerator, and we can start the experiment. This time, compared to before, you can clearly see that the free spectrum range, so the distance between the peak, is much more clean. So it's much closer to the actual device, that the ideal device is much closer. So also the performance in time, you can see they're much better. So like if you send a pulse, a very short pulse to the system, you actually see this echo that is much more clean in time. And this is, again, as before, just a cartoon picture to understand a bit better what happens. So with this system, we decide to perform the quantum entanglement in time. So this is a time-being quantum entanglement. What you do is that you send two bright pulses to create two excitation in the cavity. It's a superposition, of course, one early and one late. So the excitation travels in the cavity and comes back, and then they're again read by two pulses, two red pulses to read, one early and one late. In the optics side, what you do is that you just build a balanced interferometer to overlap the late of the direct path with the early pulse of the delayed path. So to create this type of time-being entanglement. And then, well, the beam splitter to erase the which path information, of course. So this is a very robust type of protocol for long distance information. But what we also wanted to prove is that you can coherently transport information on chip. So you can actually use this waveguide to route the information on chip, quantum information on chip. So to transfer state from this different system, heterogeneous system, because phonons can interact with several types of system on the chip, on the on-chip scale. This is the result that we did. So what you do is that you sweep the phase between the states, between this early late superposition, and you can clearly see that you have a sinusoidal interference. So this shows the coherence of the state. And we, of course, have this, again, everything that is quantum has a threshold to prove there is quantum. And this case is this entanglement witness R. There should be below 1. So again, we prove that is indeed entangled and it's coherent. So I think, yes, I'm perfect on time, even a little early, so there's more time for question. And for the next step, so like what we want to do is on the, as I said, for the 100 kilometers for the long distance is to improve the performance of the devices, to have the rate of teleportation higher. But in this side, for this phonon routing, so this connection on chip of heterogeneous system or even homogeneous system, is to have a full control of traveling phonons on the chip. So with this work, we have proven the source, the waveguide and detector, that the source is just the optomechanical cavity, and the waveguide is the phononic waveguide that we described, and the detector is, again, the optomechanical cavity. You can have two different optomechanical cavity. We used one is just for simplicity, but you can have different optomechanical cavity. So the next step is actually, we want to build and prove that it's working a beam splitter and a phase modulator for phonons to have like the full basics toolbox for quantum optics, in this case, quantum acoustic experiments. Yes, so, well, I would like to thank the whole group. It was really a big effort to all this work. This is the group now 2 years ago for the teleportation with all the people that worked, and this is a more recent picture. So the group has basically as it is today. for the people that are working more on this phononic routing. So thanks so much for the attention. And if there's question, I will gladly take that.
Thank you, Niccolo. That's a really, really interesting presentation. Just a quick virtual round of applause for yourself, for you. Thank you for that.
Thanks.
Yeah, so any questions, please feel free to raise your hands if you're in Zoom, and you can ask directly or you can enter it in the chat. And if you're in YouTube, if you type them in, then Clara can send them to me directly. So while people are still thinking, I just wanted to get one quick clarification. I think I might have missed it slightly because of some volume.
Sure.
So on the side on entanglement, when you're showing the scheme, I didn't quite understand how the entanglement is formed. So is it the delayed part? So you've got L and E pulses that are going through. That information is then encoded into the waveguides and into the cavity, which then travels into the waveguide. And the interaction of the reflected part, that's the thing that generates the entanglement?
No, actually no. So what you have is the way you create entanglement is with well, so you, of course you don't create two excitation. You create, yeah, this is where like the classical word a bit like fails to describe. You create like the superposition of these two excitation, early and late, and then to make them. So what you do is that in this beam splitter, they're still distinguishable. So if you remove this part here and you place the single photon detector here or here, you can still understand if you have the excitation that made on the early or on the late. So if one of these two pulses actually scatters a photon, for example, the early, you get a click in the early one, or if it was the late to scatter, you still get a click in the late. But once you recombine them, and these are overlapped in time, if you get a click at this time here, you have no idea. You cannot say if it was the early or the late. This is what creates the entanglement. So it's a bit tricky, but basically, like,
okay, so I see the reason you say it's in time, essentially. So
exactly, it's in time.
Yeah, okay.
So like once you re-overlap this in time, you erase this information of what of the two pulses got scattered, and then you have the entanglement in the early and late excitation in the waveguide that you can retrieve and then prove.
And is it, I mean, from an experimental perspective, is it highly dependent upon, I guess, the delay in the time, or how long can this be before that you can?
Yes, yeah, of course. So like in the experiment,
I guess it's the temporal coherence, right?
Yes, exactly. So in this experiment, like this basically gives you the idea of the coherence of the system. Like we chose to use the first reflection peak. So this gives you the time at which you send the pulses, the delay of the interferometer. It sets all these fixed experimental times. But indeed, we could have used the second, the third, whatever. We can also make much. This was lifetime limited, basically, but we can make hundreds microsecond. We can make millisecond, hundreds of millisecond devices where the coherence time is much longer, and eventually one could maybe use much longer delays and perform the same experiment.
I'm just trying to understand what the factors go into for the given experiment. What factors go into the coherence time that determine, how long a coherence time you can have?
Oh, yeah, that's a long answer. Let's see if I can. Okay, so in this case, there's several things that come in play. So the first one, well, of course, we are not lifetime limited. We can have lifetime of, if you really want to push it up to second, so in theory as good as the, well, some of the spins, but the T2 is much lower. We in the paper that I show you, the quantum memory telecom wavelength, we proved that it can go to 100 microseconds. And we still haven't measured in this system, but it could be that it's very similar. In this case, there's a problem that is given by the fact that the free spectrum range is not perfect. So this rephasing here, it can be a bit not clean. So in theory, if the free spectrum range is perfect, you have this will go back again to the maximum value here too. But since it's not perfect, you actually have a lower value. So this again will act as a loss of coherence at the end. And then there's the final limit, is that there's some defect in the surface that makes the mechanical frequency jitter. And we still have to measure if the jitter is all in phase, and in the case it's fine. But if they are like, well, it's very hard to do, but if they are not uncorrelated, uncorrelated, exactly, so they're just random, then every component will pick a phase that is different, and so they will dephase again more rapidly. This is still something that we haven't measured yet.
Thank you. Let me just check if there's any other questions.
Yeah, sure.
Okay, no, I think people are still thinking. So if there are any questions, of course, you're most welcome to email directly to Niccolo.
Yes, thanks.
And thank you so much once again for that excellent work. It's really exciting to.
Thanks to you for inviting.
No, it's our pleasure to have you. So I'll swiftly move on to our next speaker, which is Andrzej Rachowski. And he's a postdoc at Professor Radim Phillips' group in Fiaschi University. And his work focuses predominantly around levitated optomechanics, but also optomechanics in general, and pulse optomechanics and state preparation. So it's really fantastic to have him for this block. So without further ado, Andrzej, the floor is yours.
Okay, thanks a lot for the introduction. I'm very grateful for the invitation, and very nervous, and also very excited to be here and talk for this beautiful audience. My name is Andrzej. I work at the university in Olomouc. It is here on the map. I hope that you can see my slides changing. Very center of Europe. And in my today's talk, I will be speaking about generation of non-classical correlations in the levitated optomechanical system and detection of them. So I will be considering this pump and probe scheme, which is based on using of two subsequent pulses. The scheme has been known for quite a while for, I think, trapped ions. In optomechanics, this has been proposed for the first time by Sebastian Hofer and colleagues in 2011. And in this work, we essentially try to squeeze as much as possible out of this scheme in the part of the generation of the non-classical correlations, and as well in the detection of those. And one more peculiarity is perhaps that the results I'm going to show are tailored for the numbers that have been reported by the University of Vienna group, the group of Markus Astomar. Let me start from a brief introduction. I have here quite a lot of these unnecessary slides, which we perhaps do not really need. In optomechanics, we have the radiation pressure, which couples light and mechanics. The coupling is typically small. We enhance it by strong classical drive, which allows us to couple these two main participants, the cavity mode and the mechanical mode, which are really the quantum signal modes, couple them through radiation pressure in a way which is determined by the strong classical drive, which is here with its strength setting the rate of the interaction, and its tuning allowing us to change the type of the interaction between the signal modes. This talk relies on the usage of these two types of decoupling, which take place in case when the resolved-sideband condition is met. That is when the cavity line width is significantly smaller than the mechanical frequency. In this case, when we tune on a mechanical sideband, that is, if our drive field is detuned by exactly one mechanical frequency away from the cavity resonance, only one of these two interactions is resonant and the second one is significantly suppressed. So if we tune at the lower mechanical sideband, we have a parametric conversion interaction, which is also well known as a beam splitter or state swap interaction. If we tune onto the upper mechanical sideband, that is, we drive at the sum frequency, we have the two-mode squeeze interaction, which is the entanglement generating workhorse in quantum information science. Right. Okay, there are lists of last names which are very incomplete. I apologize for this. Should probably update that. Okay, so the takeaway point so far is that in optomechanics we can have this very nice toolbox of linear couplings which couple light and mechanics. So this talk focuses at the levitated nanoparticles, which are beautiful systems in which the mechanical motion is defined by the trapping light spatial intensity. This basically means that by manipulating with the trap, we can change the mechanical motion in a sense. So we can tune the frequency of mechanical oscillations. If we switch off the tweezer, we can turn our harmonic oscillator into a free-falling particle, and this is an opportunity which I think is basically unthinkable with clamped devices such as membranes or cantilevers, I think. Moreover, we can have some more interest in nonlinear potentials such as cubic one, a double well one, or maybe even more complicated. So this also, let's say, raises our interest or enhances our interest to work with levitated systems. Okay. So the takeaway point is that the levitated systems give us full potential of optomechanics and also some new interesting potentials. Okay, so now to the main content of this work. We want to send two pulses into the cavity. The first one, blue detuned pulse, which realizes two-mode squeeze interaction that generates entanglement. And the subsequent one, a red detuned one, which does the state swap. So the state transfer from mechanics to the light, which will allow us to verify the entanglement. Ideally, we want each of these pulses to do exactly its job. So we want the blue detuned pulse to perform exactly the two-mode squeeze interaction, the entangling one. And then the state swap pulse should do exactly the state swap pulse. Unfortunately, in reality, this is not so, because the two-mode squeeze in Hamiltonian, which we have, which we theorists have, unfortunately, it couples the intercavity light mode and the mechanical mode. And this is beautiful, but each of these modes, each of them is open. So mechanics talks to its environment, which means that it constantly has some noise inflow into the mechanical mode. And this noise is participating actively in the process of, let's say, entanglement creation. So the noise which comes from the bath into the mechanical mode at later times actually undergoes the very same two-mode squeeze interaction. So some of this noise will kind of participate in the entanglement creation. This is on the one hand. On the other hand, the cavity mode is also interacting with its environment. So it also has the noise inflow from the input cavity mirror, let's say. Okay, and also what is important is that this intercavity beautiful two-mode squeezing interaction, it couples mechanical mode to the cavity mode, but we don't have any direct access to the cavity mode. We only can see what leaks from the cavity. So if we want to see any correlations which are being created, we can see them only in the leaking field. And this leaking field is a multi-mode field, essentially. It is composed of a continuum of modes, temporal modes or frequency modes. It's essentially the same. And so in order to actually extract information about the correlations that are being created, we have to filter this leaking field in a smart way so that we gain the information about the correlations which are being created. Let's say, to put it simply, or maybe to give you an example, when we look at this leaking field, the stupidest thing is that it can have one of the two polarizations, right? And we have to measure this light in the proper polarization. This means that we have to fix the proper polarization mode in order to not lose the information. And the very same logic applies to this multi-mode structure in context of temporal or frequency modes. So the signal filtering is important for the detection, or let's say it is important for witnessing the non-classical correlations between the light and the mechanics. And then when we have defined properly, let's say, which temporal mode we want to measure, we have to apply a reasonably complicated measure of the correlations in order to recover, or in order to witness the generated non-classical correlations, right? I would like to illustrate this idea of filtering by reiterating the contents of the original optomechanical proposal of this scheme, which assumes resonant pulse driving at the upper mechanical sideband. So there is this two-mode squeezing interaction, and in the regime of weak optomechanical coupling, such that the coupling rate is significantly lower than the cavity line width, the cavity mode can be eliminated. Since the rates are related as such, as soon as a photon is created inside the cavity due to the two-mode squeeze interaction, this photon almost instantaneously leaks to the output mode, and in this way, the cavity mode is essentially eliminated from the system, so that the interaction takes place between exactly the mechanical mode and the leaking light, right? If this is true, then we can just write the input-output relations for the mechanical mode and one certain temporal mode of the leaking light. And these input-output relations will have exactly the form of the two-mode squeezing interaction. So exactly the interaction we would like to have. And this one certain temporal mode of the leaking light has a very certain temporal profile, which is defined by, let's say, the structure of the optomechanical interaction which takes place. So this illustrates, let me say that if we would decide to measure a different temporal mode of the leaking light, obviously this would result in a mode mismatch, and a fraction of the signal then would be lost. And this illustrates the importance of this proper temporal filtering in order to recover the correlations. Okay, this slide is probably out of place. Yeah, let me now come closer to the results. Okay, so we have this simple scheme, maybe consisting of this sequence of two pulses which enter the cavity one after another. And let's assume that we have figured out the temporal modes we would like to measure from knowing the structure of the optomechanical interaction, or say other ideas. Now, after doing the homodyne measurements, what shall we do to see the non-classical correlations between the light and mechanics? We have to figure out the necessary witness of these correlations. One very famous thing to use is the logarithmic negativity, which can be computed knowing the full covariance matrix of the optomechanical system. So the light pulse plus the mechanics. This is a necessary and sufficient condition of entanglement. So as soon as there is positive negativity, the system is entangled. However, it requires essentially the full tomography of the quantum state, which can be costly. So we would like to use a simpler thing, which is the two-mode squeezing in the optomechanical system. This is the criterion which can be a sufficient condition for the entanglement. And it can be stated as follows. If you have a covariance matrix of the optomechanical system, so system of light plus mechanics, from this covariance matrix, we can estimate its eigenvalues. And if the smallest one is below the short noise level, whereas individual eigenvalues of both mechanical and optical modes are above the short noise level, this means that the state shares some non-classical correlations. What is important about this minimal eigenvalue is that it can be recovered from knowing only 3 elements of the covariance matrix. So we can think of a generalized quadrature of a bipartite system, which is written as a weighted sum with these weighting factors, cosine and sine, of certain quadratures of each of the participating modes, where these are quadratures written in some certain optimal basis. So in order to, if we figure out this optimal basis, then the variance of this generalized quadrature is going to be equal to the minimal eigenvalue of the covariance matrix and will directly show us the non-classical correlations if this variance is below the short noise level. What is important is that this variance can be expressed from only 3 elements of the covariance matrix, and measuring that requires significantly less effort than measuring all 10 independent elements of the covariance matrix. Okay. And so we propose to do exactly that. We propose to figure out these optimal angles from the theory and then recover the correlations by performing homodyne measurement of only 1 quadrature of each of the modes. Okay. So now let me jump directly to the results. So first we evaluate the correlations which are initially generated between the first pulse and the mechanical mode. So we evaluate them by computing independently the logarithmic negativity in the system. This is the red curve, and the two-mode squeezing, which we use as a witness of non-classical correlations. Here they are plotted as a function of the heating rate, which is the viscous damping rate of mechanics times the mechanical, times the occupation of the mechanical bath. So this is really the rate at which thermal phonons enter the mechanical mode from the bath. In units of the cavity line width, these dashed vertical lines show the experimentally relevant values which are achievable in the setup which we were aiming for. So what we can see from this figure is really that our witness manages to capture some non-classical correlations, manages to capture the same non-classical correlations as the logarithmic negativity does. Okay. Yes, this plot is for this stage where only the first pump pulse entered the cavity. So what was after the generation stage, right? And then we have the second pulse, which swaps the mechanical state to light, and then then the correlations which were created during the first pulse, they now leave between the pulses. And now we evaluate these correlations between the pulses. Okay, the blue line here just repeats what was before on the previous slide. So this is the two-mode squeezing between the first pulse and the mechanics. The red curve shows the two-mode squeezing achievable between the 2 pulses, the first and the second, the generation and the readout pulses. Solid line means perfect detection efficiency, and the dashed line stands for the detection efficiency of, I think, 40%. This shows that this technique of detecting non-classical correlations is actually quite feasible given the heating rates which are feasible in a state-of-the-art experiment. Okay. Again, as I said, in order to perform the detection of the non-classical correlations in this scheme, we have to figure out the homodyne angles, which have to be set to see the quadratures which are correlated. And this here shows the dependence of this squeezing on the imprecision of the homodyne angles. So let's say if we set the angle of the homodyne, if we step away from the optimal value of the local oscillator phase for the detection of the correlations here, then here is the squeezing which we will achieve. Different colors stand for different initial occupations of the mechanical mode. Green is 1 phonon, blue is 10, this yellow is 100. Probably have to note that levitated systems have been shown to, have been cooled to close to the ground state, to mean occupations even below 1 phonon. So given such cooling, this green line turns out to be feasible. And this kind of proves that this technique should be feasible in real experiment. Okay. Yes, so now what concerns the optimization of generation of the correlations. So this is the work mostly done by Alexander Pitchford, who is now has a permanent position at Aberystwyth University. Many thanks to him. In this part of the work, we do essentially what follows. We construct a black box in which we put our simulated experiment. We feed into this black box a set of control parameters, which in our case are lengths of the pulses, coupling rate as a function of time, optomechanical coupling as a function of time, detuning of the light, which controls the type of the interaction, also as a function of time. And then this filtering function, which is, this filtering function, which is essentially the local oscillator amplitude profile as a function of time, which allows us to filter out the temporal mode shapes at the output. Yes, in order to see that one mode to which the mechanics couples during the entanglement generation. And also these homodyne angles. In order to recover the optimal quadratures which are being correlated. So we have this black box. We have this black box and then a computer which runs the optimization of the experimental parameters. So how this works is that this Bayesian optimization thing, it can send this set of control parameters into the black box and see a figure of merit as the output. In our case, this is the two-mode squeezing. This work has been done within the collaboration called the blind quantum control. So in principle, it should not matter whether this black box is a simulated experiment or a real experiment or whatever. It should just work, optimizing the figure of merit as a function of these control parameters. And I think it did actually. So here are the results of this optimization. So if we consider the simplest scheme in which we just drive the optomechanics with rectangular pulses of constant strength, so which essentially means just constant coupling rate for a fixed amount of time, then the optimization the optimization quite confidently converges to some very precise results. If we then expand the parameter space to feature if we expand it to include different filtering functions at the output, so measuring different temporal modes, we immediately gain some fractions of a dB enhancement in the correlations generation. If we further allow the coupling rate to be a function of time, we get a further enhancement here. And if we add the detuning to this parameter space, it allows us to obtain even further enhancement of the correlations, which is shown by these green parts of the histogram. Then if we add, let's say, if we simulate some real experimental parameters drift by adding some randomization at the simulation, the results, the results get worse, but they still mostly outperform the original noiseless scheme with the constant coupling rate. And here is the important thing. These are examples of the optimal profiles of these functions. In particular, here is the filtering function, which differs quite a lot from what we would expect from simpler theoretical models of the optomechanical interaction. This sort of means that this smart or stupid optimization procedure is capable of generating stronger correlations than a smart theorist, which figures out these filtering functions based on their vision of the structure of the optomechanical correlations. Okay, with this, let me finish. I hope that I have convinced you that levitated nanoparticles are capable of exhibiting some non-classical correlations, which can be read out, importantly, which can be read out with less effort than a full tomography would require. So, yeah, thank you for attention. And I would be happy to try answering questions if there are any.
Sorry, thank you, Andre, for that, and a virtual clap for the excellent piece of work that you've shown us today. I suspect people are still digesting some of the information, so I'll kick off. I always have too many questions, so I'll ask with one. And this is actually just a clarification. It's a really interesting point you mentioned earlier, which is about filtering signal. So from an experimental point of view, I have a levitated system which has various modes, and when you put a detection, or when you try to detect the different modes, it's often very difficult to separate that detection out. So it's very difficult to separate detection of individual modes. And you'd have to do filtering afterwards.
Okay, do you mean detection of filtering of different mechanical modes?
Yeah.
Oh, I guess this is even...
So, but the thing is that when you... So I maybe this is where I didn't quite understand what you meant by filtering. I got the impression you meant... I didn't quite understand. Were you talking about the mechanical modes itself that you're filtering out? Because you're doing a pulse measurement, which will have encoded in it multiple modes of information about multiple modes.
I would say that like the system which we consider is multimode in a variety of ways, right? Like if we focus on the intracavity interaction, we have their optical field and the mechanical field, which are both multimode. And the standard optomechanical theory usually focuses on just one mode of light and one mode of mechanics for the intracavity interaction. And this is already, let's say, a subset of the problem that you mentioned, because you have multiple mechanical modes. But like my problem, which is inside the cavity, a single mode problem, when I consider how it couples to the outside world, to the leaking light, it couples to a variety of the leaking light modes. So, like to put it in a stupid way, let's say if it leaks a photon, this photon can be created at different times, and this gives us different sort of temporal modes for this photon. But this is at the particle level. Here we work with the continuous variables, and continuous variables. So we want, do I have an equation for that? Okay, this one. let's say, the correlations which are being created, they generate some quantum information which constantly leaks outside of the cavity in the form of the instantaneous value of the field outside. And this is this A out of T thing. When we do a detection, we essentially integrate this field, overlapping it with the homodyne profile. And as a result, we're going to obtain a superposition of the instantaneous, maybe not superposition, but a combination of the instantaneous values of the leaking field with some weighting factor, which allows us to convert this multi-mode field into just one signal mode of the output. Does it make sense?
Yeah.
This is the filtering which I mean. So the way how we what I mean by filtering is exactly this process of assembling the instantaneous values of the leaking field into one single mode. Let's say if you have just a cavity without any mechanical parts and you have a single photon living inside, if you let it leak, the photon will likely leak into a temporal mode with exponentially decaying envelope, I think, or exponentially rising. And so if you want to register that single photon, but not with an APD, but let's say if you want to do some very ineffective detection by, let's say, homodyne detector, you would probably like to perform some temporal mode matching of your homodyne profile with the temporal profile of this leaking photon. And this is once again that filtering which I mean.
I understand. Okay, no, thank you for that.
Well, I think this addresses one important thing which I wanted to explain, but probably failed. So thank you for the question. It, I think, fits very, very precisely.
So there's a question from Clara. Clara, do you want to ask your question?
Hi, and thanks for the very nice talk. Really nice criterion to characterize entanglement. I have a question about this criterion with the minimal eigenvalue. I was wondering if this works more generally, or if this is something that you can do in the specific setup where you have the two-mode squeezing and the beam splitter, or if I can apply this more generally, because this is, I mean, it's really nice because you don't have to calculate the logarithmic negativity or something like this. So, is this something that only works for this specific?
Yes, I can give you a very hand-wavy answer. Like, we are happy that our non-classical correlations are generated by exactly the mechanism of the two-mode squeezing, so we can see it in the smallest eigenvalue. So this is good. On the other hand, this is a like this criterion which we use. It can be recast to a form which matches more or less closer to this EPR variance-like thing from the, also known as Duan's criterion, right? The idea is that Duan's criterion is quite strict, quite a strict thing, which is very strictly proven. And in our case, it's more like a witness, which very well suits exactly our mechanism of creation of the correlations.
Okay. But then again, I suppose as long as you have a linear problem in the sense that everything is made out of two-mode squeezing and beam splitting, probably there's always a convenient basis to rewrite things so that you can use this criterion, I would imagine, right? I could imagine it. This can be quite more general.
I mean, I'm afraid of generalizing this unnecessarily far.
Yeah. Okay. But anyway,
I mean, it does make sense. It definitely does make sense to me what you suggest, but I would still, leave some room for myself to not give precise answers.
Yeah. No. Sure. Thank you very much.
No, thank you for the question.
Okay, thank you. I'm just conscious of time, so I think we'll wrap it here. And of course, if anyone has further questions, they're most welcome to contact Andre directly. Thank you once again, Niccolo and Andre, for joining us today, and everyone in audience at YouTube and in Zoom. We'll publish the date for the next block, which will start next month, which will focus on, oh my God, my memory's failed me. Clara, Marcus, can you help me? It will focus on superfluid optomechanics. Sorry, yeah. Superfluid optomechanics, so really interesting and exotic field of optomechanics. So I look forward to having talks from there. And until then, please have a great and a safe month. Catch up soon. Thank you once again.
Thank you. Bye.